Patootie, Math Angel. Welcome back. This is Decaf-Math ASMR. I hope that you're doing well today. Today I am going to go over a cute little proof, and this topic is from set theory. Set theory. But you don't have to know very much about set theory to follow along today. Maybe just some basic concepts and notation. If anything, this is really more of an exercise for proofs by induction. Let me go ahead and just write that out. Proof by induction. Proof by induction. Just in case you happen to want to look up this proof technique for yourself, we're just going to go through each step and apply it to this statement here. Before we get started, I wanted to take a little extra moment to remind and encourage us that right here and right now, it does not matter what your relationship with math is, even whether you feel like paying attention to this or not today. This is meant to bless us right here, right now. You can totally just use this to study and review, or just for a bit of nostalgia if you've heard of this before, and if this is just a walk in the park for you. But you are equally welcome to just sit back and relax, zone out, or even just drift off to sleep. If you do fall asleep, you won't get in trouble here. I won't get mad. It's not offensive. This is just our little math nook space to just enjoy, take our time, be in peace. So there's no sense of comparison. There's no such thing as being smart or dumb. It doesn't matter. We don't have a deadline. There's no pressure. So we're just going to be present, okay? That's my only little prayer for now, is that we're just covered in love. And that's also where my excitement for this kind of thing really does shine most. And so I just want to share that here today. Okay, so with that little note, let's get started. So we are proving that every set with n elements has 2 to the power of n subsets. Every set with n elements has 2 to the n subsets. Okay, so first of all, what is a subset of a set? So if I have a set, a subset is just a part of that set. It's a piece of it. So if every element in my subset also is an element in our original set, then I have a subset. Okay, so for example, if I have a set 1, 2, 3, 4, okay, and this is our set notation. We put 2 little curly brackets and our elements go inside if we have any. And by that I just mean there's a special case where we have just the empty set with no elements. And so if this is a set, then a subset could be something like this, 1, 4. So 1 is in our original set, and 4 is in our original set. So 1, 4 is a subset of the full set 1, 2, 3, 4. And the original set is called a superset. Okay, so it's like if it fits inside of my original set. So 1 like this is also a subset because this element is also inside here. Okay, so as long as every single element in my subset is also in my set, then it's a true subset. So I didn't want to digress too far, but this is obviously a very important thing to note since it's part of our statement here. And just a little side fact that we will need to know is that the empty set, so a set with no elements, is a subset of every set. And the set itself, so in this case 1, 2, 3, 4, is also a subset of itself. So any set is a subset of itself. So these are kind of the two extremes, I suppose. First of all, it's a little weird to think that an empty set is a subset of every set, but it kind of is true. It doesn't go against what we said in the definition of a subset, right? So technically, every element in my subset, there just happens to be no elements, is also in my original set. You can think of it that way. So note that I just kind of did this to show that it was nothing, but that's not to be confused with the set that has 0 as an element. This isn't 0, this is just an empty set, okay? So that is a subset of every set. And also, technically, the set itself, any set, is a subset of itself because technically every element in a set is still an element in that same set. So it still satisfies this, okay? So just keep that in mind because we will be relying on that fact in a little bit, okay? But that's just kind of fun fact to think about. Just by definition of subset here, okay? Okay, so every set with n elements, so we're just using this as a general fact. It's not very deep into set theory, but it's just a cool thing to think about. So if I give you n elements, any number, just within reason in this context, we're counting the number of elements, so there are not going to be negative elements, like a negative number of elements rather. The elements themselves can be negative, but we're talking about n number of elements. So this can include 0, which we'll talk about, but these are counting numbers. It's going to be 0 or bigger, so at least 0, so no negative number of elements. And if I give you any n, there will be 2 to the power of n subsets. So for instance, if I have a set with 5 elements, there will be 2 to the power of 5, which is 2 times 2 times 2 times 2 times 2, which is 32. There are 32 subsets. So that's what this means. If I just give you any n within this context, I can tell you that there are 2 to the n subsets. Alright, so let's get to proving here. So the first step in a proof by induction is to confirm a base case, to show that the base case is true. It's not really a proof, it's just a writing out the logic to confirm that it's true. Usually the base case has to do with n equals 0 or n equals 1, but not always. I'm thinking here 1 definitely works, but I believe n equals 0 is the most basic of base cases here. So we're going to do n equals 0. And so we are going to say show true for n equals 0. Alright, so what does that mean? We need to show that a set with 0 elements has 2 to the power of 0 subsets. So what is a set 0 elements, that would be our empty set. There are no elements, right? So now, how many subsets does the empty set have? It's a little strange question because how can we have a part of an empty set? Well, the empty set is a subset of itself technically, and the empty set is a subset of all other sets, and so this is really truly the most base case you can get. The empty set is a subset of itself, the empty set. So the empty set has one subset, i.e. the empty set. Okay. And 2 to the power of 0 equals 1. I'm pretty sure that's all we would have to say, because this indeed implies that, well, it doesn't prove anything, it just shows that for n equals 0, that this is a true statement 2 to the power of 0 subsets. If I have 0 elements, we have one subset, and 1 is equal to 2 to the power of 0, so this is true. So just going back intuitively a little bit, I know it's a little weird to think that the empty set might be a subset of the empty set, but you can just rely on what we said earlier, that the empty set is a subset of all sets, including the empty set itself, and that any set is a subset of itself, so the empty set is a subset of the empty set. I know it's just a little weird to think about like nothingness being a subset of nothingness, but it still counts, right? It's still a part of any set. So however you want to explain it to yourself, this is indeed true. So that's all we really need to show here. We just write out this logic in some type of way. So that's good. Base case is good. Now, step 2 for a proof by induction is to assume that the statement is true for n equals k. K is just like an index, and we'll come back to the intuition behind proof by induction here in a little bit, but we're just going to pick an arbitrary k, and we aren't going to do anything with that. We're just going to assume that this is true. So assume true for n equals k. Okay, so if I give you some k, I'm going to just say, okay, this statement is true. So there's nothing to prove here. I'm just going to write out the assumption. So a set with k elements has 2 to the k subsets. So if I give you a particular k, I'm saying that this statement is true. I'm just going to assume that it is true. Okay? Assume true. Okay, so that is just going to be accepted here. Now, there's nothing else to really do in this step, but we are going to set this up a little bit so that our next inductive step is a little more clear, so that we can walk through the logic there more clearly. So I'm going to actually go ahead and break this down a little bit before we go to the next step, okay? But this is really all you need to write for the assume true part. Now, what does this actually mean? Let's think about some of the subsets here, okay? So let's say I have a set with k elements, okay? It doesn't really matter what those elements are, so I'm just going to generalize the different terms here. And just to index them, I'm going to write A1, A2, A3, until AK. So depending on what k is, we just can generalize any set this way to show that there are k elements. If k happens to be 0, we have our base case, and so it would just be the empty set, because we would have 0 elements. If k happens to be 1, then I'd only have one term, which would just be a1. If I have 2 terms, I would just do a1, a2, but then otherwise you can just go as far as you need to a k. So this is just a general way of representing k elements, because if I count 1, 2, 3, 4, until k, then that would be k numbers. That's why I don't start with a sub 0. I start with a1, just to make this very clear that there are k elements. Okay, so let's think about what some of these subsets might look like. So for starters, we said earlier that the empty set is always a subset of any set, so we have at least one. And we also said that the original set itself is also a subset, so we have at least 2 here. Okay, but what about some of the others? So we can have, for instance, a one element subset, right? This is a subset of this whole set. We can do it for each of these, a2, a3. These are each individual subsets, ak. Okay, so that's allowed. We can also pair some of these up, so we can do a1, a2. We can do a1, a3, a1, ak. Something to note is that for sets, the order doesn't matter, so a1, a2, and a2, a1 are the same set. But that doesn't really matter. We're not really listing every single subset here. I'm just trying to get some of the pattern, some of the idea out. So that's one pairing, but we could also do a2, a3, a3, a4, There's so many here, and you can go ak minus 1 to ak, right? You can do ak minus 1, comma 1, a1, whatever. Okay, so you can do 2 element subsets, you can do 3 element subsets, right? Like so. So it's a good thing that we are not trying to actually write out every single subset here. Okay, that is good, because it would be very hard to keep track. But the one thing that we do know from this assumption is that the total number of this is 2 to the k. And that's all that really does matter here. Total number of subsets is 2 to the k. Okay, but this is just to get an idea of some of these. So empty set, 1 element subsets, 2 element subsets. I guess I would have to take extra time with some of this indexing to make sure I'm not double counting some of this. Like I said, if we have the repeat, but again, the actual pattern doesn't matter right now. We just know that the total number of these subsets is 2 to the k. So we are assuming this to be true. We're assuming our statement is true for the specific case of n equals k. Alright, so why do we care? Because the next inductive step, so number 3 is the inductive step. And that means that we are going to show that this is true now for n equals k plus 1. So we assumed that this was true for n equals k. But now, using this fact, we are going to prove that this statement is true for n equals k plus 1. So I'm going to write out want to show that a set with k plus 1 elements, like the number of elements is k plus 1, has 2 to the k plus 1 subsets. Alright, so this is where I think the logic gets really interesting. So one thing to think about, let's write out this set perhaps so that we can visualize it. So just like we indexed the k element set, we are going to index this set. We might as well. So this set with k plus 1 elements, I might as well write it as a1, a2, a3, dot, 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 ak, and then ak plus 1. And I'm just writing ak just to make it very obvious that we are building off of our k element set here. And now we are going to add another term, one more term, okay? And that's going to be an important part of this logic. So what does this mean? Well, how many subsets are there for this set now? So we knew and we assumed that there are 2 to the k subsets of for a1 through ak. So there are going to be there are 2 to the k subsets of this whole set with k elements without a sub k plus 1. This k plus 1 element set without a k plus 1 as an actual element, because our k element set is in and of itself a subset of this a k plus 1 set. So if I have k plus 1 elements, then I also have this subset that has k elements, and there are 2 to the k subsets here of this part, because we assumed that we said that a set with k elements has 2 to the k subsets. And when we wrote out some of these, this is just the point to get the idea here, these subsets all are just up to k, or ak, a sub k. Here I'm adding this a sub k plus 1 part, so there are the same 2 to the k subsets as before that don't have this new a k plus 1 element. But if I now have this one extra element, I can just take all of the original 2 to the k subsets and add on a k plus 1 term. So instead of the empty set, I can have, let's just do this temporarily here. I can have a k plus 1. Instead of a1, I can have a1 comma a k plus 1. I can just add on an a k plus 1 to each of these in a one-to-one fashion to make another bunch of subsets of this next bigger set with an a k plus 1. So there are also 2 to the k subsets that have a k plus 1 as an element. that covers all of the subsets because we have this k element subset, and there are 2 to the k subsets of that subset. And then if I think about just adding one more element, how does that affect all the other subsets? Well, the original subsets are still subsets of this bigger set, but then we can also include another set of subsets, or just another grouping of subsets that contain this new AK+1 element. I hope that that makes sense. You can take some time to think about it if you want to. So therefore, the total number of subsets of this k+1 element set is 2 to the k plus 2 to the k. So we have 2 to the k for the ones without AK+1, and another 2 to the k for the subsets with AK to the +1, because I just added that element to each of them. And so that equals, let me just do a little bit of algebra here. You can factor out this 2 to the k, and you get 1 plus 1, or you can write it as 2 times 2 to the k, whichever way you want to do it. It's 2 to the k times 2, and with just some basic exponent rules here, you can think of this as 2 to the 1. So you keep this base of 2, and you do 2 to the k plus 1. Ta-da! And that's the result that we want. We want to show that a set with k+1 elements has 2 to the k+1 subsets, which we just did. Ta-da! So we had to assume that this n equals k part is true, and then we used that assumption to do this part. And then we just added a k+1 as an element to each of those 2 to the k subsets to cover all of the subsets of this full k+1 element set. And then that works out to be 2 to the k+1. Isn't that just so interesting? I think this is really fun. This was a fun thought here. So why does this induction proof work? So first of all, I should mention you just need to do these 3 steps, and then you can just say, therefore, by proof, by induction, this statement is true. We've proved it, okay? So you do need to have all 3 pieces, though. You can't just do this part, or, just confirming a base and do this. You need all 3 together to do a proof by induction. So just for the intuition behind what's actually going on here, there are different ways to think about this, but this is the way I like to think of it. If you start with the base case, so in this case we're doing n equals 0, but you have to kind of apply it to the question you're looking at. That's like the first index, okay? So now we're going to assume this is true for n equals k. So k is just, I like to think of it as an index. So for instance, if I just assume that this works for n equals k in general, and then I use that assumption to show that it works for n equals k plus 1. It's like whatever index I have, k plus 1 is the next index, the next number, right? So if I can do that, then I have this sequence of indices that are all true. So if I have my base case, n equals 0, and I set k equals 0, well, it works for n equals 0, so it also works for n equals 0 plus 1, which is n equals 1. Then if I kind of think of resetting k as an index to 1, then, and I say, okay, assuming that it works for n equals 1, it also works for n equals k plus 1, so another n equals 1 plus another 1, which is 2. Then it works for n equals 2. but because it works for n equals 2, I also showed that this is going to work for n equals 3, etc., etc. And then since it works for 3, it's going to work for 4. If it works for 4, it's going to work for 5. Because if it works for k, and I just showed that it always works then for k plus 1, then the next one will always work. Well, if this works for 0 and 1 and 2 and 3 and 4 and 5, etc. infinitely, then indeed it works for every set with n elements, and they will always have 2 to the n subset. So every, right? So I'm not showing this directly. I don't have to write out every set with n elements ever, which you can't do, and it's infinitely many, right? But we can kind of imply this by saying, here's a base case, and if it works for this, it's going to work for the next one, and if it works for that next one, it's going to work for the next one, because I assume it's true for one. Then if I can use that assumption and prove that it therefore works for the next one, then you can just keep chaining these together. You can also think of it, going backwards, also back down to your base case, but this way is more intuitive to me as to why you start with the base case, then you assume, and then you build into the next one. I hope that this was interesting if you happen to be trying to follow along. I think this particular logic is a lot of fun, especially with the sets and subsets here. But there are a lot of different applications of proof by induction. There's some fun algebra ones as well, but this is just a classic example from set theory, so I thought this was a cute little proof. But yeah, I will leave that here for today, and if you are asleep right now, I'm wishing you sweet, sweet mathy dreams. If you're going to continue on with the rest of your day, I hope that it is a good one. And thank you for tuning in today, and if you are looking for any particular topics, I will be continuing to jump around. I'll be doing some ASMR and math and ASMR, playing around with ASMR some more as well, of course. I have lots of different topics on my channel so far, and we'll keep building onto our library. And if you've been here from the start and have been supporting me, I really appreciate it, and I appreciate your patience too, because I do jump around a lot of different topics here, and it's kind of interesting getting to know the people that swing by, so I tend to tailor that. So anyway, we will keep building, and I will see you around very, very soon.